Hello, I'm Francis and thanks for watching this video. We are going to be talking about the theory of plate tectonics, which is basically an extension of the continental drift theory, an idea that was developed by Alfred Wegener in the early 1900s. Today, these two theories serve as a foundation upon which we understand the geologic processes that shape the Earth. According to the theory of plate tectonics, the lithosphere, which is the rigid outermost shell of the Earth, is broken into tectonic plates, which you see here. You can call them tectonic plates or lithospheric plates. It's important to note that some plates are oceanic, some are continental, and some are a combination of the two. As illustrated in this diagram, the topmost part of the lithosphere is the crust, and we can identify two types of crust here. The first one is this gray part here, which is called the continental crust. It's thick and less dense. It's less dense because it's made up of the rock granite. The dark gray part here under the ocean is the oceanic crust. It's very different because it's much thinner and more dense. It's more dense because it's made up of the rock basalt. Now this together with this brownish part here, which we call the rigid mantle, are what make up the lithosphere, the solid outer part of the Earth. Now keep in mind that beneath that is this layer of partially melted high viscous material called asthenosphere, and so the plates that we live on are actually floating on the asthenosphere beneath. Now, down in the asthenosphere, this molten material is able to move, and it moves because of a process called convection. Essentially, convection says that hot material becomes less dense and rises, and when it rises, it cools down and becomes more dense and sinks. And so what we end up with are these circular rising and falling and sinking convection currents, which we call convection cells. Those end up being the force that drives the motion of the plates. In this diagram, we have a type of a boundary called a divergent boundary, where the plates are ripped apart by the convection beneath. Here's a map showing the plates, and as you can see, there are quite a number, including African, South American, North American plates, just to name a few. These plates are separated by boundaries and they move relative to each other. And what that means is that there's a lot of action where these plates meet. For example, that's where we find all our earthquakes, shown here with purple dots. That's where we find all our volcanoes, shown here with red triangles. And so all seismic activity, earthquakes, volcanoes, tend to happen at or near these tectonic boundaries. Which brings us to those plate boundaries and the different types. Now, it's important to note that things happen when two plates interact with one another. Now, we need to know what those interactions look like so that we can know what to expect. And there are basically three types of these interactions, which give us three types of plate boundaries. We have a transform boundary, where two plates slide past one another, as shown by the arrows. A convergent boundary, where plates come together, and a divergent boundary, where plates move apart. We should be familiar with the various things that happen at these plate boundaries. Let's look at some examples, and we're going to be using this map that shows plate boundaries. We'll start with transform boundaries, and these are boundaries where plates slide past each other. As you can see in this animation, you notice that there are two plates which are moving in opposite directions, sliding laterally past each other. And in the process, we get a lot of pressure buildup, a lot of grinding, which is often released in form of earthquakes. Transform boundaries don't tend to have volcanoes or mountain ranges. The only real feature we see along these types of boundaries are earthquakes. This is an example of a place you can see a transform boundary on the surface. This is the San Andreas, and it's found in California. It's the one responsible for earthquakes risks in cities like San Francisco and Los Angeles. Let's go back to this map and try to identify a transform boundary. There are several of them, but the most famous one would be the San Andreas, and it's along the western coast of North America, shown here. The next type is the convergent boundaries, and this is where two tectonic plates meet or move towards each other. Now, in this type of boundary, we have to consider not only the fact that two plates are coming together and colliding, but what type of crust involved. For example, we see different things happening when it's oceanic crust colliding with oceanic crust, as opposed to continental colliding with continental, and so forth. And so we have different types of convergent boundaries. The first type is called the subduction zone, and as you can tell from this animation, this happens when a continental crust on the left collides with an oceanic crust on the right. As you can tell, notice that oceanic crust is sinking beneath the continental crust, and that's because the oceanic crust is more dense than the continental crust. It's heavier. And when it sinks, it melts because it's hot down in the asthenosphere, and the melting rock finds cracks and crevices to rise to the surface, forming active volcanoes. And so the features that we look for along subduction zones are a chain of active volcanoes, and tall mountains, a deep ocean trench that's shown by this dark line of the coast, as well as lots and lots of earthquakes happening along the subduction zone. We also have an island arc, which is similar to a subduction zone. The only difference is that these are two oceanic plates involved. It's a bit hard to tell which plate is going to subduct, given that they are of the same density, but eventually one plate, usually the older rock, subducts beneath the younger one. And again, we have this melting which causes magma to rise, forming volcanic islands. We also have oceanic trench and lots of earthquakes. In this map, the example of a subduction zone we are going to look at is the Peru-Chile trench. This is a subduction zone because the two plates involved here are Nazca plate, which is an oceanic, and South American plate, which is a continental plate. And so that gives us a subduction zone. Finally, we have divergent boundaries, and this is where two plates drift away from one another. Again, we have to consider the type of crust involved. If it happens on land, we have what we call a rift zone, where the land rips apart into two. We see this happening in East Africa, along the East African rift. When the rock rips apart, it allows magma to escape, and so we get active volcanoes along the boundary, and as well as some minor earthquakes. If divergence is happening in the ocean, we have a mid-ocean ridge, as shown here. The plates are pulled apart by convection currents, magma rises, and forms active volcanoes and minor earthquakes. Something important to note here is that the younger rock will always be found near the ridge, because that's where the magma is cooling to form new rock. As you get further from the ridge, the rock age increases. This proves that the rock is diverging. This phenomenon is called the seafloor spreading, and it became a key evidence supporting the theory of plate tectonics. The most common mid-ocean ridge is the Mid-Atlantic Ridge, which you see here, right in the middle of Atlantic Ocean. It actually extends all the way north. It's the most common mid-ocean ridge, although we find them throughout the other oceans of the world. And that's a summary of what we need to know about the theory of plate tectonics, one of the most fundamental theories of physical geography, and one that serves as a foundation upon which we understand the geologic processes that shape the Earth. Thanks for listening.